Hello everyone, I'm glad to have this opportunity to share with you our recent progress in kinetic investigation on HiPIMS discharges. I'm Bocong Zheng, and I come from the Fraunhofer USA Center Midwest and the Michigan State University. My research interests are in plasma simulation, especially particle simulation and discharge physics. In this presentation, I will first briefly introduce the particle simulation, and then apply the particle simulation method to magnetron sputtering, while using a one-dimensional simulation for HiPIMS, and in turn investigate the HiPIMS discharge characteristics, electron kinetics, and gas rarefaction using particle simulation. So the greatest advantages of particle in-cell Monte Carlo collision simulation is that the PIC simulation is fully kinetic and can provide a self-consistent and complete description of complicated plasma discharge behavior. I developed an efficient plasma simulation software based on the PIC simulation. The name is Astra, which is electrostatic and capable of simulating plasma discharges in 1 and 2 dimensions. Astra has been successfully applied to the simulation of low-pressure, long mean-free path particle beams and atmospheric pressure on microplasma discharges. Astra is also used to simulate radiofrequency discharges and magnetron sputtering discharges, which we will talk about shortly. Now here we present a brief schematic of a typical magnetron sputtering setup. The plasma was generated in a chamber above target surface. The magnetic field distribution in the simulation region is illustrated here. Here we use a typical balanced magnetic track with the highest magnetic field parallel to the target surface of more than 200 Gauss at around x equals 3 centimeters. The target could be dielectric or metallic for radiofrequency magnetron and metallic for direct current magnetron. Here we show some typical voltage waveforms commonly used in magnetron discharges, that is, radiofrequency and direct current and pulsed DC with a frequency in the hundreds of kilohertz, and high power impulse magnetron sputtering discharge with a very small duty cycle and a very high power density per pulse, ensuring that the time average power density is the same as in the DC case. Well, due to the E times B configuration, the magnetron discharge is essentially two-dimensional or even three-dimensional. However, multi-dimensional particle simulations are time-consuming for conventional magnetron discharges and almost infeasible for HiPIMS discharges. So let's take a step back. Could the one-dimensional case be used as a reference to qualitatively study the discharge characteristics of magnetron sputtering? Because the simulation time for the one-dimensional case is much smaller than that for the multi-dimensional cases. So here we performed a two-dimensional simulation of conventional DC magnetron sputtering, and we select the one-dimensional region above the racetrack, where the discharge intensity is also the highest. We performed a one-dimensional simulation along this line. In order to maintain similar discharge intensity, we drive the discharge with a current source such that the current density is similar in 1 and 2 dimensional simulations. From the results, we can see that the plasma densities, the electric potential, the ionization rate, as well as the electron mean energy in 1 and 2 dimensional simulations are very similar. We also diagnosed the electron energy probability functions in different discharge regions, and it is found that both 1D and 2D simulations capture a typical discharge characteristics of DC magnetron sputtering, that the electrons have a boosted high energy tail. The EEPFs in the bulk plasma region are almost identical, while the differences in the cathode and anode sheath regions have little influence on the discharge. So with the assumption that one-dimensional simulations can qualitatively capture the HiPIMS discharge characteristics, now we examine the HiPIMS discharge using the one-dimensional PIC simulation. In HiPIMS discharges, due to its high power density and strong sputtering, additional physical processes should be considered, such as the Coulomb collisions between charged species, the sputtering wind, that is, the gas rarefaction caused by momentum exchange between the sputtered species and the background gas, and the metal ions, ionized from the sputtered species, and the secondary electron emission induced by these multiply charged metal ions. Here we present a one-dimensional simulation considering all the above-mentioned processes. The discharge parameters are as follows. A discharge voltage of -1 kV, a working pressure of 1 millitorr. The working gas is argon. The target is copper. The gap length is 3 cm. The trace particles include the electron, the argon atom, the argon ion, the copper atom, the singly charged and the doubly charged copper ions. The top right plot gives the variation with time of the discharge current density on the target surface. The current density is in logarithmic scale. We can see that the total discharge current increases exponentially with time, and the slope of the increase rises significantly after roughly 9 microseconds. At the same time, the current carried by the copper ions increases rapidly and replaces the argon ions as the primary fraction of the discharge current at about 12 to 13 microseconds. The singly and doubly charged copper ions carry about the same magnitude of current. Similarly, the bottom right plot gives the variation with time of the spatially averaged number density of each species. It can be seen that after 9 microseconds, when the discharge current is rapidly increasing, the background gas argon is significantly consumed due to the strong ionization and the sputtering wind, which will be discussed later. And after about 12 microseconds, the copper ion replaces the argon ion as the dominant ion in the plasma. And we all know that this is the key indication that the discharge has entered the HiPIMS phase. Next, let's take a detailed look at the spatial-temporal evolution of each species during the HiPIMS discharge. As seen from the spatial-temporal profile of argon atoms, before about 10 microseconds, that is, when the discharge current is not yet very high, the dominant species in the discharge region is argon atom, which is the case of conventional magnetron discharge or conventional weakly ionized plasma. However, after about 10 microseconds, the plasma density and the number density of all the other species increase significantly. The electron density could be up to 6 times 10 to the 19th power per cubic meter. During the phase of rapid increase in discharge current, that is, around 10 microseconds, the most dominant charge carrier is still argon ions. We observed a high-density argon plasma throughout the discharge region, and the density peak of argon ion at around 11 to 12 microseconds, during which time the density of argon atom is significantly reduced due to the loss through ionization. The density of copper ions peaks after argon ions because the density of copper atoms grows significantly upward only with the significant increase of the discharge current through sputtering. For both argon and the copper species, extremely high ionization fractions that are nearly fully ionized can be achieved during the HiPIMS discharge phase. Next, let's take a look at the electron kinetics. First, we need to understand the spatial-temporal profile of the electric potential. It can be seen that the sheath region decreases during the low current discharge phase until about 10 microseconds, when the discharge current increases sharply and the discharge enters the HiPIMS phase with the formation of a wide pre-sheath layer. Note that the electropositive ion sheath is still very thin during the HiPIMS phase. The top right figure shows the variation of the ion sheath width with time obtained from the space charge distribution, which can be as low as 10 micrometers in the discharge in the HiPIMS phase. The electron energization or electron heating mechanism can also be deduced from the electron power absorption profile, the J.E. If we take the sheath position as the dividing point and count the electron power absorption in the sheath region and the bulk plasma region, we can see that the electron energization mechanism at low current stage as sheath energization due to the secondary electron emission heating, and at high current HiPIMS discharge stage, there is a transition to direct ohmic heating in the ionization plasma region. The bottom right figure gives the electron energy probability functions at different times. During the low current stage, the EPF is not much changed. We can observe a typical bi-Maxwellian-like distribution, that is, a low energy group with a boosted high energy tail. While during the discharge runaway phase, that is, from low to high current density, around 10 to 11 microseconds, the EPF becomes a Maxwellian-like distribution. When the discharge enters the high current stage and the copper ions replace the argon ions, the EPF is bi-Maxwellian-like again. Finally, let's take a look at the gas rarefaction phenomenon from kinetic point of view. The left figure shows the spatial temporal flux of each species during the discharge. The electrons are repelled from the target surface as expected. The background argon atoms during the discharge current transition stage are strongly repelled from the target due to their momentum exchange with the sputtered copper atoms from the target. This phenomenon is also called the sputtering wind, which is theoretically believed to play a role in gas rarefaction. Now, from a kinetic point of view, we see that there is at least some effect at the near target region. Well, for the ions, theoretically, they should be attracted back to the target. That is why the HiPIMS discharge generally has a lower deposition rate. Well, this is true for argon ions. For singly charged copper ions, due to the copper atoms sputtered from target surface have an initial velocity away from the target, the copper ions ionized far from the target have a chance to overcome the pre-sheath potential and leave. For doubly charged copper ions, due to their stronger confinement in the pre-sheath, it's difficult for them to leave. The right figure shows the reaction rates for the momentum exchange between argon and the copper, the electron impact argon ionization, copper ionization, and the ionization from singly to doubly charged copper ions. It can be seen that the strong ionization of argon atom throughout the discharge region is the primary reason for gas rarefaction. The peak position of ionization to doubly charged copper ions is far away from the target surface because the electron temperature is higher here. So this is the end of my presentation. Thank you for your attention. The slide can be downloaded through the following link. You are also welcome to contact me at these email addresses. And if you are interested in this topic and want to get more information, you are also welcome to visit my personal academic page at bczheng.com, which has more detailed descriptions of my research. Thank you very much, and please let me know if you have questions. Thank you.